You're fine. I'm gonna turn on my sound.
Hello. Hello, hello.
Yep, I can hear.
Yeah.
Perfect. Audio is good too. All right. And do you want questions, interactive, or do you want it at the end? What would you prefer?
I don't mind questions on the go.
It's just harder because if it's on the go, that means they need to yell it because it will be hard to.
Yeah, then let's do it.
At the end.
Yeah.
Okay.
Yeah.
Then I'll talk about that, and before we start, I'll just quickly introduce you and
Yeah.
just same as Mike's.
Thanks, Jacob. Do you know where the bathroom is?
The box. Yeah, I have seen this. This
Yes, yes. What am I? Yes. I have no idea when. When looking for it in the morning, find out. And then about the day. Yeah. I probably also.
Yeah, I was able to use, I said. I don't really know what sushi. I don't really, this is what it is. So it's like, yeah, it's. Looking forward to it.
Yeah.
I was sure. So it looks like. Yeah, I'm not sure it counts. I'm not sure it's totally. It's still. It's. So it's evidence.
We're gonna start in a minute. We're gonna start in a minute, so if you could gather yourself at the seating, that would be nice. Thank you.
Should take a picture then. Maybe together with Jehan and Mello as well.
or the 10 minutes for the tutorial together?
Yeah,
Yeah, we can do it at the end when the Jinghui gave the talk. Yeah.
Oh, thanks for coming.
You good to start?
Yeah.
Okay.
I hope Zoom is working.
Yeah, I can see the Zoom is so
Cool.
good. So we're gonna start. So our next speaker is Vlada Rozova. She's a postdoctoral research fellow with the Center for Digital Transformation of Health at the University of Melbourne. She's a data scientist and machine learning practitioner passionate about developing automated systems that can facilitate clinical decision making. Vlada works with stakeholders of diverse backgrounds to build solutions that address user needs and enjoys seeing the development and implementation of tools from start to end. I'll leave it to Vlada now. As usual, just now with the question Q&A, let's leave it at the end and give like 5-10 minutes for you all to ask questions. One last housekeeping thing that I should mention just now: there is actually a toilet just in this little hole here. So if you've been walking around finding toilets with me, you don't have to. It's just over there.
Thanks, Jehan. Everyone can hear me, see my slides, so we can get that sorted from the beginning. So this next hour will be a bit more hands-on, but not really. I'll be hands-on, you all will be watching. Just to give you a taste of what clinical NLP in practice really is, and I think it's a nice follow-up to have we figured out the GPUs and large language models. We have not, that's why we still do this very sort of rule-based-ish approach. So I will be guiding you through an example where we will be building a named entity recognition tool for clinical text data. And you've got two links here. You've got the link to the dataset that we'll be, which I'll show you in a second. And there will be the QR code in a second again. And then the link to the Jupyter Notebook, which you can download if you want to run it locally. What we will be talking about, we'll be talking where to start and what to look out for when we work with real-world clinical data. What are the common approaches and what to expect from each of that. And the approaches are probably very familiar to you, but I guess there is a clinical spin on that as well. And how do these different approaches compare against each other again? So first, let's take a look at the data, and you can use your QR code reading abilities. And I'm just going to click that link. There you go. All right. So one of the platforms Mike mentioned is called PhysioNet, which provides a number of data sets. A lot of them are EEG data, which is readings from our brains, but also clinical notes, discharge summaries, and so on. So this isn't a ruthless self-promotion. It was just the easiest thing to use. This is a data set we published earlier this year with our colleagues from the Royal Melbourne Hospital and the Peter MacCallum Cancer Centre. And this is a data set of cytology and histopathology reports. Okay, so I don't expect you to know what that is. We're just going to look at that now. But in general, you log in and you can look at different data sets and you can access them once you've signed all the data use terms. So it's a credentialed access. You can't just access it out of the blue, but if you've signed some conditions, then you should be good to go. It's free. And so what we have here is we have, well, first of all, 2 folders, annotations and reports, and then some license stuff, whatever, and then a metadata CSV. So if I click on the metadata, that's just a summary with unique report IDs and some other information that might be relevant for development. And then if we go to the folders, we've got some number of reports here, each in an individual text file. That's roughly what it looks like. And we'll take a closer look later. And also annotations. So annotations are in this ANN format. I don't know if you're familiar with that. There is this great, slightly clunky annotation tool called BRAT, and that's BRAT produces these ANN files. If I click on one, that's what it looks like. So the phrase is long, its character position is 185 to 189 in the report, and it's the category that was assigned to it is sample type, and T1 is just an ID. That's a really, there was just only one concept report that got annotated, so that's easy. Maybe if we look at another one ways more. Yeah, this report has a few more annotations. So that's the general sort of idea of what the data looks like. Okay, now say we've got now access, we've downloaded that, that's what we now have on our laptop. Now over to the Jupyter Notebook, and I'll just run it on my laptop, but again, you can fork the GitHub repository. The GitHub repository has all the code. If you want to try and reproduce some of that, it also has these slides, and if Mike and Jigme want to add those slides there later, we can too. And the outline of the notebook that we'll be looking for is roughly the following. I'll give you some more background on the dataset we'll be working with. We'll do a little bit of exploratory data analysis just to get an idea of what's in there, how many reports, and what do they look like. We'll talk about how to annotate the dataset. So this dataset is already annotated, but trust me when I say it was a painful process to get to this point. And then we'll look at 3 different types of named entity recognition systems and basically compare them, see what works well, what to expect in every particular situation. And I'll wrap up with some other tips and considerations. So if you click here, it'll take you to the GitHub repo. Tutorial Jupyter Notebook is the one I'll be opening as well. If someone is not familiar, this is a Jupyter Notebook. This is what data scientists and other developers use in the day-to-day life. And it is able to read all sorts of code. And I know a lot of my colleagues, clinical colleagues, get very excited about Jupyter Notebook. All right. So first thing first, we'll get to know, it's called CHIFIR, cytology and histopathology, invasive fungal infection reports dataset. And again, just a little note that you can't access it without signing the agreements. And that's really the only way you can convince your ethics committee over at the hospital to share the data to the public, right? And that's what we are really trying to do with our group, because we think there are, as Mike mentioned, there aren't enough publicly available healthcare, good quality data sets. So some background on what is happening here. Cytology and histopathology reports are reports produced by pathologists. They're free text, and depending on the sample, on what the report contains, it might vary quite a bit. So basically, it's all the macroscopic and microscopic observations that a pathologist makes while looking at the sample. They might dye it with some special chemicals to visualize particular structures, cells, tissues, you name that. And then they'll describe what they see. And they will also describe what they haven't seen. if they think that's relevant to the context. The premise of all this and of developing this data set and the problem we're trying to solve is detecting invasive fungal infections, or we call them IFI. And so the trouble with IFIs is that they're quite rare, but if happens in a person with a compromised immune system, in our case, these are patients with blood cancers or stem cell transfers, that's pretty deadly for them. They can't really fight that back. You as a healthy individual will probably never even know or notice, but for them, that's a big trouble. And detecting these IFIs is a bit difficult. Like, it's not straightforward. There isn't a single test that you can just run, like a blood test. Rather, you have to look at different pieces of information, and that sort of is what Mike was talking about, temporality. You have to look over a period of time at different pieces of information, and a clinician would have their own inbuilt system that weights these pieces of information differently to eventually produce basically a yes or a no, whether the patient has IFI or does not. So histopathology reports are one of these pieces of information. They can give us an idea of whether something is happening, but they never give us 100% certainty. So even when we talk about histopathology reports, even when we develop classifiers, we talk about, suggestive of IFI. We don't say it's positive. We never know. It's got to be taken into account with other pieces of information. And so I mentioned the aim is to detect these IFIs and to build a tool that can accurately detect it. And part of that is being able to tell whether a histopathology report contains evidence or not. Because that's, if you think, is really the more sort of labor intense part of it. You have to read a whole report. You have to analyze what it's saying. If we could just summarize it to a simple, maybe. This can be done in 2 steps. That's what we're sort of exploring here now, is we can first try and extract any relevant information, whether it's positive or negative. We just want to extract the relevant bits, the phrases that describe fungal organisms. And then based on this information, we can classify a report as suggestive or negative for IFI. So that's sort of contrasting to maybe a bag of words model, or any model that takes the whole of the report and just dumps it into an algorithm and produces a probability score straight away. You try to break it down in 2 steps. And one of the reasons to do that is that clinicians love AI. They love putting it into the grant proposals, but they're also very hesitant about AI. So they're like, let's do cool AI stuff, but also we can't really trust it. So maybe good job developing it, but maybe let's park it for now. So what you want to really do as a machine learning person, as an NLP person, you want to build something that's easily interpretable. And by sort of splitting this task into 2 subtasks, that gives you an opportunity to present them with this extracted information first, that you later dump into a classifier. It sort of offers some interpretability then. So we'll be focusing on the first task of named entity recognition, and which is, what does it mean? It means detecting words or phrases in the text that describe a particular concept, right? We'll, I hope, know what named entity recognition is. And of course, since it's free text reports, and since we're at an NLP conference, we're going to be doing some NLP here. But let's first, of course, look at the data set itself. So I'm going to so remember we have a folder with reports, a folder with annotations, and this metadata file, which I'm going to load. And I'm going to have a look at it. What does it have there? It's got a patient ID. It's got a report number, a label for the report, and a unique ID for each report. And then it's got the 2 columns that are sort of suggesting the optimal split of the data for the development. We'll talk about that in a second. So how many reports? 283. If you've worked with like loads of Twitter data or massive data sets coming from, I don't know, publicly available data, Wikipedia news, all that, we don't get to experience that much. We have 283 reports, and as Mike said, clinicians are very pricey. So annotating 283 reports was like really a good achievement. You wouldn't be able to afford much more than that, probably. These 283 reports are coming from 200 patients. So we make a mental note, okay, some patients have multiple reports. We need to make sure that we handle that correctly during training. How many? Up to 6 reports per patient. What's with the report level annotations? So 243 reports were annotated as negative for IFI, and 40 reports are annotated as positive for IFI. So that's our end goal that we want to predict one day. So that's 86 versus 14%. Okay, so it's not too imbalanced, but it's not. Accuracy is probably not going to be your best metric here, right? We want to keep that in mind too. So the data set has the recommended data split into the development test sets. And it also has recommended data split for the 10-fold cross-validation of the development set. So if you want to compare multiple different approaches, especially if you're comparing, say, a simple machine learning model with a neural network that you would be training in very different ways, you want to make sure that you split the data in the same way every time, because otherwise your results might just be better because the data split was better for this particular scenario. So what we did, we just appended it to the data set so that people can reproduce it and compare it to what our results. So yes, that's the tip here that I just spelled it all out. So the reports themselves, this is going to be a tiny bit interactive as well, because you'll have to read the reports again. But I didn't bother and print them out like Mike did, because I don't know, I'm not as good of a person. Freeze, I don't know. So we're going to load the reports from that folder. And let's take a look at one of them. I hope you can see. I'll give you 20 seconds to just quickly look at it. And I guess think, what can you note to yourself? Or as an NLP person, what do you think is special about this report? Anything? There is some, isn't there? And it's exciting because that means that you can section and look at particular sections in case this is relevant. The other thing is, you probably noticed are those long strings of X's. This is, the report has been de-identified. Small sort of note on the side, de-identification algorithms are still very clunky, and the algorithm I used here is called Vlada. Vlada went through every report and like, replace this with X's, because that was the most reliable method for the relatively small amount of data. We can, as Jehan mentioned, we can see different sections and section headers and caps lock, which is great because maybe we can just focus on one of them. And finally, of course, as any clinical text uses abbreviations and quite specific terminology. So an example here is stage 4 FL on bispecific AB. I don't know what that means. You probably neither, but more importantly, our computers might not know what it means. So we need to somehow resolve that. So let's go back to Jehan's point that the report is structured. Are they all structured in the same way? No, of course not. Why would they be? Some formatting got lost while, you know, my clinical colleague was copying this from the EHR system onto an Excel dataset or spreadsheet from where I was unloading it here. Headers vary sometimes, and I can't have an explanation for that. Sometimes I feel like a clinician would bring up a template that they need to fill in, and then they would just rename some sections just out of the, I don't know, spite. So, you know, what seems like the most important section, the diagnosis here, was called an opinion in the previous report. Can be conclusion, can be anything else. So let's look at the length. Hopefully they're not too long. Ooh, that's not good. That's not good. Sorry. Yeah, fair enough. Right. Okay. There might be other problems later, but the report length is up to 4,000 characters. So again, making a mental note, not every transformer model would be able to handle that. You might need to split it into smaller chunks. How do you do that? Do you do this based on sections, for example, with variant headers or somehow else? Same goes to report length based on the label, positive or negative. Is there any correlation? No, there isn't. They're just, to me, these distributions are pretty similar. Okay, so let's go now through the annotation process. So imagine you are myself 1 year ago. You have 283 reports that you've gone through and de-identified. And now you need to build a classifier, and you need to build a named entity recognition tool. So where do you start even? How do you annotate these reports? And you have at your disposal 2 medical experts, but they've never done this before. They have no idea what a named entity recognition is about or how to do that either. So what we're going to do, we're going to try and sort of think where to even start and what to annotate. And for that, we're going to take a look at another report, and I want you to look at it and try to identify any phrases that you think are related to fungal infections. And no prior knowledge is required here, just some sort of ability to read would suffice. Question mark fungal? Yeah, so that's actually one of the favorite tricks, the question mark and then condition. It's like all-time favorite. There need to be a separate tool for resolving those, because that's what I think, but I don't know. So please, you know, confirm my my idea. That's a query from the referring doctor. We also have, in the microscopic description section, we have fungal elements, and then again later on fungal elements. And so with the fungal elements, I think one thing I want to emphasize is they're both explicitly negated. So it says no fungal elements are identified, no evidence of fungal elements. So we want to capture both. We want to capture the fungal elements itself, but then we want to also capture that it's negated. Finally, actually, pneumocystis, and I've been training to pronounce this word, is a type of, it's a species, a type of fungi. And then grocot. Grocot is a chemical, a dye that a pathologist would apply to visualize fungus. So if we look back, you can see here it's saying no pneumocystis or other fungal elements are identified on the grocot stain. So definitely very negative, but a lot of information that's relevant that we want to pick it all up. Now, what did I do? Okay, so we have some idea of the types of information that we might be looking for, right? How do we, I guess, what is it? Let's try and summarize it. It's what the referring doctor suspects. It's the stains that are used to examine the specimen, because just the mere fact that this stain was used tells you that actually they must have been suspecting something. It's the explicit mentioning of organisms or species. That's very helpful, obviously. And of course, it's whether any of that was explicitly negated. And so after kind of going back and forth with the clinical team, and I want to emphasize this is a very iterative process, and it's iterative in its development, and then they start applying this schema and they come back to you and they say, I have no idea how to categorize this new phrase. Let's alter the schema. And you say, okay, let's do it. But now you have to start from the beginning and apply it so that it's consistent across the whole data set. Lots of frustration on both sides. But after some time, we sort of arrived to this annotation schema. So 9 concepts: a concept for queries, a concept for a category for descriptors, like fungal elements. It's not very specific. It doesn't tell you what exactly it is, but it's a descriptor. Particular species names, invasiveness. We're talking about an invasive fungal infection, so we want to know whether it's spread. Names of stains that were used, sample type, because we actually care where it is. We care if it's in the lung or in the skin or, I don't know, anywhere else. And then 3 types of certainty cues or certainty terms: positive, equivocal, and negative. And that sort of relates to what Mike was showing in the previous hour, that pathologists, radiologists, they do tests and they write reports, but they're not actually working with the patient, right? They don't know the whole context. They don't know the whole picture. And so they're really unwilling to commit to something. I can understand that. They don't really know what's happening. This is what they're seeing, but they don't always know the whole picture. So they would use sometimes very evasive sort of terminology, which it's maybe there, but also maybe not. But I think it's there. It's quite possible, but also unlikely. And so you have to somehow try and discretize this into preferably yes or a no, or at least a yes and maybe and a no, or that's 6 grades that Mike was presenting. So there are flavors, and we try to capture these flavors in these 3: positive, equivocal, and negative. So if we think back to our example, we can then categorize those phrases that we were able to detect, right? So the question mark fungal would be a clinical query. Fungal elements would be fungal descriptor. Pneumocystis is a type of fungus. Grocot is a stain. And no and no evidence of are both negative, right? That's how we would, now that we've worked through an example, you and I, we can annotate this that particular report. Now, if we were to come up with a new report, And this is sort of an illustration of training annotators. If we were to come up with a new report, we would be able to identify and categorize these words because we know them. So I want you to take a look at a new report, and I want you to try and tell me whether you think it's positive or negative for IFI. Again, just based on your sort of feeling. Negative? Anyone else? You think it's positive? Anyone else? Negative?
As it has identified fungal elements, so it has to be positive.
Yeah. So the phrases we already know, pneumocystis, it says there is no evidence of pneumocystis, right here. It says it's clearly negative. However, of course, if we were to go to our medical friend and ask them for help, they would tell us that this report contains a whole lot of references to fungal infections. Fungal hyphae is a fungal descriptor. Interestingly, this whole construction of thick, non-septate and branch at 90 degrees is a very specific descriptor of fungal infections for pathologists, because it's describing this tree-like structure that's growing, God forbid, in your lungs. And aspergillus is another type of fungus. It's a name. So the first two would be fungal descriptors, and the latter would be a fungus. So if we were to go back and look at it, well, there is no evidence of pneumocystis, but there is, the morphology is suggestive of aspergillus, right? And it says that the smear contains scattered fungal hyphae. So you'll have some negated concepts, some non-negated concepts, and you'll have to make do with that. So I guess this is just to illustrate how we build our knowledge base, how we build our, if you will, a dictionary of different concept categories and possible phrases describing them. So now that we have this additional knowledge, we can definitely say it's probably positive. So after going back and forth, as I said, multiple times, we finally managed to annotate the whole of 283 reports in a consistent manner, where the same annotation schema was and the same rules, the same sort of logic was applied to each report. And we refer to these as gold standard. That's what we provide at PhysioNet. And that's what you can use semi-reliably, obviously, to train your own named entity recognition. So I will just load them here. And below is the table summarizing what has been annotated. It's a big table. It gives you some examples. That wasn't a good idea. It gives you some examples of what different concepts look like, different concept categories. So for example, equivocal is my favorite. Atypical, possibility, possible, really hedging the bets there. A few important things to, I guess, pay your attention to is, for the same equivocal category, there are only 7 occurrences in 283 reports. So hoping to learn something from that is maybe a bit of a stretch. You're probably not gonna, your tool is probably not gonna perform very well with equivocal concepts. Another thing to pay attention to is lexical diversity. And lexical diversity is the ratio between the number of unique phrases to the total occurrences, right? And if the lexical diversity is small, like for example, in stain is a great one. 172 occurrences, only 13 of them are unique. So it's very likely to be something you've already seen. The lexical diversity is low. You're probably going to be able to learn it, to machine learn it pretty easily. The contrary situation is with clinical query and invasiveness, both of which have quite high lexical diversity, not as many occurrences. So that might be a tricky one to deal with. So just to sort of summarize this section a little bit, some considerations for when doing named entity recognition in general and on clinical data in particular is obviously the size of your data set. We only have 283 reports, and some concept categories are pretty sparse. So you need to be realistic about what you're gonna end up with. Lexical diversity, which I guess Mike talked about it as well. There may be more than one way to say the same thing. And I guess the flip side of that, there may be one thing talking about many different concepts. Is that the question? Yes.
Is certain lexical diversity taking like different sections of different counts?
Here, yes. All of that counts as unique. Yeah, you could probably like just take the stem and then you would have better numbers, but presumably it's affecting each category roughly similarly. I don't know. It's a good question. All right, and the last bit is very specific, narrow subject, so and sort of related to limited utility. Both pre-trained models, deep learning models, any other pre-trained models, and terminology sets or like knowledge bases might be too generic. And with, so by terminology sets or knowledge bases, I'm referring to, for example, MetaMap, which does cover a lot of medical concepts, or all of them more or less, but it's just not granular enough for this particular problem, because this particular problem is very granular. So you might just need to work on a smaller scale because of the problem that you're trying to solve. All right, and then now we'll just look at 3 named entity recognition tools as promised. The first one is a dictionary-based approach, very simple. We kind of have just done this together, but basically you look at an example, you construct a dictionary of possible phrases for each concept category like we did after passing the first report, and then that's your dictionary. And then you try to either expand it or apply it as it is. So that's our dictionary after passing the first report. After going through the second report, we add some more phrases to the fungal descriptor category. We add aspergillis to the fungus category. Okay, we have a bigger dictionary now. We are likely to pick up more terms. If we were to stop here, that would be, these 2 reports would be our training data naturally. And then this would be our learned dictionary, right? And so the remaining 281 reports, we could just treat as unseen test data and apply it as it is, or we could keep passing more reports and sort of expanding, bulking up this learned dictionary. Once we are done with that, we take our truly unseen report, preferably from somewhere hidden far enough. And importantly, we do any pre-processing we do needs to be the same, obviously, as with the training data. So tokenization needs to be consistent. And we scan the report to find matches with the learned dictionary. And then if there is a match, we just record it sort of somewhere so that we can then compare it with the original. What to expect? So I think that's the more important bit. Poor performance if the training set is small. which means you haven't seen enough examples of various ways of saying the same thing. Also expect poor performance if lexical diversity is high. And this, of course, includes spelling mistakes, which in clinical data are prevailing, I would say, above anything else. Expect good performance if the language is consistent and if the context doesn't play much role. So if you're just after picking out, I don't know, a very particular word anywhere in the report without any negation, without any context, then you'll be probably fine. You'll be very fine, by the way. But if context does play a role, then dictionary-based approach wouldn't work there. Very easy to interpret. That's a great thing about it. If you work with someone from non-technical audience, you just like show them, look, that's what I knew, that's what I found. It's very easy. It's very interpretable. And if you want to visualize it, you know, your workflow for maybe clinical review, that's very helpful. Conditional random fields is a very popular, very common model used in named entity recognition. It's a machine learning model, but it's a rather simple one, so it's a good sort of middle ground. How does it work? Well, let's think a bit about the context. So we know that some phrases are rather unambiguous, such as scientific names of fungal species. If it says aspergillus, it's probably just meaning that. But then other words can have more than one interpretation. And an example I came across a lot in these reports is the word organism or organisms, because it can be referring to a fungal organism, which I care about a great deal, but it can also be referring to bacterial organisms or viral organisms. And I have no idea which, like, I really need to know which one it's referring to, but the dictionary-based approach would totally fail here. Or like if it says organisms of fungal origin, it might just not pick that up. Sorry, mental blank. So, oh, that's not fitting very nicely. Yeah. So a CRF model, what does it do? It allows us to take into account some contextual features. It allows us to build a list of attributes for each word and then make a prediction based not just on the word itself, but on its attributes. And that's really the gist of it. So we're trying to augment our word with some additional descriptors that hopefully capture the some contextual or spatial relation and hopefully capture what we actually are trying to capture, its relatedness to invasive fungal infection. So which features to include? You can include a great deal of features. A lot of them might not be useful, might be. So that's really goes down to proper feature selection, feature engineering when developing your CRF model. But it could be, you know, the start and end character positions in the document. It can be different capitalization patterns. Does it start with a capital letter? Is it written in caps lock? And so on and so forth. Morphologic patterns like the first 3 characters, the first 2 characters, the last 2 characters, so prefixes and suffixes. Any numeric or punctuation patterns like is it hyphenated, does it contain a digit, and so on. You can play around with that and come up with very creative ways of trying to capture what you want. Are the common attributes part of speech tags, sentence level position, preceding or following words explicitly can be also encoded as features. So lots of things to think about. And then again, once you've trained your model, so I guess this list is what we've included, but yes, you can explore further. Once you've trained your model, you want to apply it to unseen report. Again, make sure you tokenize the report in the same manner, and make sure you compute attributes where possible for each token in the same manner again. And then the predictions are made both based on the word itself, its attributes, but also on the predicted label of the neighbors. So this means the CRF model is kind of able to take into account some small neighborhood of your word. What to expect? Expect good performance when linguistic structure is consistent. So these contextual dependencies are consistent across the documents. Expect poor performance if you chose your attributes poorly, basically, or if the attributes are not computable. So, for example, you trained your model and you have two attributes, preceding word and following word in the sentence. And you've trained your model and the model gives really high weight to these two attributes. And then you have a new sentence, but the new sentence only has one word. So you can't compute the previous and the following. And so then the model is probably not going to work because it won't have anything to start from apart from the word itself. Still quite easy to interpret. You can say which attribute gives like how much weight towards the prediction. So that's great again. And so before we move on to the third approach, which I think you can guess is something deep learning-y, let's just quickly look at the sort of major levels of linguistic structure. And I stole this from Wikipedia. But basically, it's sort of breaking down linguistics as a study into these concentric circles, into these different branches of science. And each branch is dealing with its own level of complexity. So you start with phonetics that deals with speech sounds. You move on to phonology, which is dealing with phonemes, which is both probably not relevant to NLP. But then once you go into morphology, which operates in words, and then syntaxes, which starts putting together some words into phrases and sentences, and then semantics, where you start inferring some meaning, yet literal, but meaning of these phrases and sentences. And then finally pragmatics, where it's like the most high level, broad meaning in the context of discourse. So looking at this diagram, I thought maybe I could draw this analogy that we have different models that operate at different levels of this linguistic structure. And before I clarify this idea, just quickly, how does a transformer work? A transformer works by splitting the text into tokens and subtokens and mapping them into some numeric vectors. That's what we call encoding. And then the encoding for each word depends on the word itself, but also on its neighbors or other words in the document. So the context is much broader than in CRFs. It's sort of the window that you can look at is much wider. And then there is this great, the real sort of advance in deep learning in NLP is the attention mechanism that helps you to understand, actually, which neighbors should I pay more attention to and which ones I can sort of ignore-ish. So that's like a very intuitive, that's how I understand transformers anyways. And so then I thought, okay, then we could say that the dictionary-based approach operates at the level of individual words, sort of like morphology. And then CRF starts to slowly dip into syntaxes. It starts to sort of take into account the closest neighbors and maybe put together some little phrases. And then a transformer model allows you to take a leap to the next level to semantics by handling these large, long-range dependencies and sort of starting to almost infer context out of the free text. So with transformers, you can train your own, but that I think isn't a very common practice nowadays. There are lots of pre-trained models. And again, going back to the point of limited resources, both development and implementation computational environments, we probably often cannot afford to train our own transformer model, also small data sets. So instead, we're likely to take something that's been pre-trained for us, and we're going to just fine-tune it a little bit for our particular task at hand. BERT is the most sort of popular architecture, in my understanding, and there are lots of different flavors. Of course, Jinhui will then talk about for an hour about many, many different other transformers that I can't keep that all in my head. I just know BERT. And then I know that there is a BioBERT and a PubMed BERT and a clinical BERT and a discharge summary BERT. And I've got 10 minutes. That's great. I don't need that many. And they all were trained on their own large databases. And so I guess one of the sort of decisions to make for you as a developer is to pick your flavor or flavors, but some finite number of those. There is a heap of models, pre-trained models available out there. And you sort of need to decide based on your text that you're working with, which ones are going to be more similar. So for example, pathology reports, I don't even know, probably clinical BERT would be the best because it's using EHR notes, so like progress notes and from electronic health records. Or maybe BioBERT because it's learned all these species from large biomedical corpora. And then, of course, again, as always, the key step is to make sure your pre-processing is the same as what the people that pre-trained this model for you did. And I think that's something that gets omitted often when a new model is published and released and hey, it's so cool, you can use it. But you actually cannot use it because you have no idea what exactly step by step did the authors do to their data. So I guess we expect good performance if the annotated dataset is generally similar to the data used in pre-training. So our custom little dataset is similar, at least-ish, to the data used in pre-training. We expect poor performance if the amount of data is not enough, even for fine-tuning. And I wouldn't be able to say how much is not enough, but I imagine that in some situations, if you have like only a handful of reports, 100 of instances, you won't be able even to fine-tune very well. Obviously non-trivial to explain. If anyone works in explainable AI, please tell me how, because if I were to present that to my clinical colleagues, they'd be like, that's a black box. How do we know what it's doing? Let's go back to that first dictionary-based approach, because that was really, really easy to understand. And we can talk about it everywhere at all our symposiums. And now to the comparison. So that these three models, and on the GitHub, we have the code for all three. If you want to have a look at it and criticize our coding, please do. If you find a mistake, please submit a pull request. But these are the three models, the precision on this data. And I guess one thing I want to note is the precision of the dictionary-based approach. The precision of the dictionary-based approach is quite low. And why that? That's again because we are not taking context into account. So if we've learned the word organism, we're going to pick out this word organism every single time, regardless of whether it's a fungal organism or not, which means we're going to have a whole lot of false positives, which means our precision would be relatively low. The CRF and BERT both seem to be handling that a little bit better. Note the equivocal category, none, like just non-existent. throw it away. Don't even bother. Recall, on the other hand, I'd say the dictionary-based approach is a bit better than CRF. It's and I don't quite know why. Maybe the CRF is a bit too restrictive, so it's almost not flexible enough. So it's missing some. Sorry, someone.
Oh, sorry.
So it's missing some occurrences quite a bit, especially in the sample type and positive and negative. Annoyingly, because I'm a very conservative person as I'm learning about myself, BERT is actually performing better than either of the first two. So I guess we'll just have to use transformers this time. So just to wrap up, and I mean, Mike named most of it, I think. So the negation detection NEGEX algorithm developed by Wendy Chapman in 2002 is still great, has an implementation in SPACY, works like a charm, can modify it as well. Something to think about is whether we can also detect uncertainty or affirmation, because maybe we want to distinguish between a pathologist just mentioning a concept and a pathologist being strongly confident that this is present. Again, talking about the flavors of certainty. And you can, by the way, you can modify the NEGEX algorithm to do that. So the tools Mike mentioned, MetaMap is a knowledge base. A pre-trained CRF or transition-based model like SPACY's named entity recognizer is basically a CRF. And it's got a bunch of derivatives like MedSPACY that Mike mentioned, but also SciSPACY that was trained, I think, on PubMed as well. And MedCat is this sort of hybrid of rule and machine learning based models. You can pre-annotate the data before feeding into clinicians, which might or might not make your life easier. So you can, for example, use MetaMap to annotate the data, then give it to clinicians to review that, and then maybe the outcome would be better. But it might be worse or more tricky to resolve. Because they go down the rabbit hole, they start arguing with it, they're like, oh, maybe it's right, maybe it's wrong, I don't know, we need a committee to sit down and think about it all together. So it might make your life harder. And finally, relation extraction and concept linking are, I guess, the next level where you could go naturally after named entity recognition if just recognizing entities is not enough, right? You would want to try to link, is this staining this particular fungus? Is this no evidence relating to this particular fungal infection, and so on? And so that's, I think, also pretty important. And that's all, and I'm 1 minute left. Great, thanks. Thank you.
Any questions?
Very much, that was very informative. So you keep talking about how it's very hard to get the right amount of data. Where does synthetic data fall into this, knowing how complex, like also knowing how complicated the clinical most can be?
Yeah.
But are there any attempts or other way of using synthetic data?
So do you mean synthesizing the reports themselves, or do you mean?
Yeah, I mean, especially with large language models coming up and so on. Is that a possibility, or is that something that?
It's a good question. I actually don't know if I have the answer to it, if anyone else does. I imagine synthesizing sort of reliable, free text, medical, accurate data would be a challenge. And then you still face this issue of annotating it, right? You still need to present a clinician with the report to annotate. But at this point, you might just take the original one so that there are less questions. Yeah.
Don't forget to introduce yourself.
I am Duke from UNSW. I guess I have one question, one comment. So number one is, you know how you have different categories for the different descriptors?
Yes.
And that's like, so you have like, and so for every single report, you have to manually add in the different concepts for each of the descriptors, right? You know, what if you have a concept that is in two descriptors?
Then you're in trouble. So, and that happened. And I think you have to, I think one of the solutions is you make a choice. So for example, the word fungal, as we saw, can be a clinical query or can be a fungal descriptor. And so what we did, we said, okay, if it's both, pick what we think is more important. We think it's more important to identify fungal descriptors. Ideally, well, I guess it means that you're not doing your job well enough, really. It means that you're not resolving these two well enough. Because if a human being can resolve it, then you can resolve it. You're just not taking enough context into account, probably.
Yeah. And I guess the one comment I'd like to make is you mentioned how when you have spellings, when the notes have spelling mistakes, then that decrease the accuracy of performance. So I'm just wondering if you considered using edit distance to correct further spelling mistake.
Yeah, so spelling correction, I think, is one of the steps you almost always have to do with clinical notes. The trouble comes from, so you need to correct, you need some reference, right, to correct. So you compare between what you have and the true kind of spelling, the correct spelling. The trouble comes is with building this reference list of terms, because it's just hard to obtain. I don't know. I've done quite a bit of that, and you can't just use general English language because they wouldn't have all the terms, and they also wouldn't have abbreviations. So you don't want your algorithm to correct abbreviations, because abbreviations are not wrong. They're correct, but they wouldn't be known to the dictionary. Does that make sense? So it's an important step, but it's got its own tricks, I guess. That's my answer.
Good one.
Thank you so much. My name is Kalina. I'm not from Union, but I work in the industry. By the way, great name for the dataset here, and like another question I have a similar problem with the personified database. For example, you have personal data like name, addresses, and sometimes they can be actually used as a descriptor, and they could be important for diagnosis. For example, if you have an outbreak of fungus in particular postcode, but you don't see it because database is personified, you're kind of in trouble. Or sometimes when you remove the name, you lose gender markers, and like your condition is gender specific or ethnicity specific, something like this. So how would you go about that?
Well, I think the idea of identifying, personal identifying information is that in general, it shouldn't affect our diagnosis, and it does very often. That's why we have a lot of biases in our data. I think with removing name and losing the information about the gender, you could first derive the gender and then remove the name. But that, of course, assumes that you can do that somewhere inside the hospital within the infrastructure that has probably no resources for that. So it's all a bit of a fairy tale that we can extract reports, de-identify them straight away, and then pass them from hospitals somewhere else. The reality is I'm affiliated with the hospital so that I can access the reports, do what I need, then de-identify them, and then share them to the public. So it's a bit of a flipped process. Yeah. Postcodes are not, I don't know, I thought postcodes are not pH high, so you can actually keep that. Yeah, if combined. So there are, I think, gray area situations where, like, if it's just postcode, it's fine. But if it's combined with other bits, then you're in trouble. Yeah.
Thank you so much.
Thank you.
All right, let's have a 10-minute break and we'll come back at 3:40. Good. Uh-oh.